Alright, so before we actually look at the equations of lines, algebraically or anything like that, I want to actually illustrate kind of what we're talking about, but I need 2 volunteers. Good question. Never volunteer for something you don't know what you're doing. You're just going to be illustrating motion. Alright, so I'm going to have one person stand over here, one person stand over there. Alright, so Jay, you'll need that one, you'll need this one. Okay, so each of these guys has a starting point. Go ahead and stand on the post-it note there, over in the corner. They have a post-it note. We're going to use the tiles here on the floor as our coordinate plane. And for the purpose of this, we're going to be facing, that's our positive y, okay? That's positive y. So we'll be walking to our right to go positive x, to our left to go negative x, take a step back to go negative y, forward to go positive y, okay? Now, I gave each of these guys a different velocity vector, okay? So Eric, what's your velocity vector?
-5, -2.
All right. So what's he gonna do?
Go back.
This way, back 10.
Okay, he's gonna come this way 5 and take 2 steps back.
I go 2 back first, so I can like.
Yeah, that's fine. And then Jay, what's your velocity vector?
4, 1.
4, 1. So you're going to come this way 4 and move up 1. All right. So, all right. Each of them has followed their velocity vector once. Okay, so this would be their position after doing that once. So go ahead and do it one more time. All right, so if you think about it, Eric started here and ended up over there, and Jay's right there. So if we were to draw their paths, would they have met?
No.
What do you think?
Yes.
I mean, it's kind of a straight line from from where Eric started to where Eric finished, and Jay's kind of right on that path. Okay, let's try it again, but let's do it this way. Try to pick the point that you're going to end up and walk in a straight line rather than going back and over. Okay, so go back to your starting points.
Wait, is he?
You can just go over. Oh. Okay. All right, so you see your point that you want to go to after the first time, and just walk in a straight line there. Go ahead. Okay. Now, see the point you need to go to for your second one, and walk in a straight line there. Okay. So you see they kind of...
Our arms touch.
Their arms touched, alright. If they weren't such hulking guys, then maybe their paths wouldn't have crossed. We don't know, okay? Here's the thing though. Can we consider just their paths in this case?
Yeah.
Wait, what do you mean by that?
Yeah, no.
Can we just consider the fact that Eric started here and ended there, so we draw a straight line, and Jay started over there and ended there, so we draw a straight line? Do they meet? Is that all we have to take into account?
The speed. Are you?
Okay.
Well, which if they, because if Jay went
If Jake
all
kept
like 6 this way first or something, then we might have. Yeah, I know. Oh, yeah, never mind.
Okay.
Like if he, I don't know. If he did, it depends on what order he would. If he didn't go in a straight line and I did,
Okay.
maybe we would have hit or something.
Maybe. Alright. What do we have to consider here? Because as I'm looking at it right now, Jay's right in our path.
Right.
But our paths cross. Do we actually meet though?
Not necessarily.
Well, because there's something at the point. If the points never meet, then they're not crossing. But the paths behind those points could cross.
Okay. So
Yeah,
what
yeah.
is he taking into account beyond just our position?
The
What?
physical form.
The physical
The item that the point represents.
Yeah, speed, but it's related to another. I mean, you have your velocity vector that I gave them, and that's related to speed.
Mass. Force.
No.
I mean,
What, Cameron?
Airtime.
Time.
Ah.
All right. In order to actually meet, it's not good enough just for our paths to cross. You have to be crossing at the same time as well. All right. So thank you. You guys can have a seat. I'll take those. All right. So here's the thing. You guys all came through that door, and I may have missed it, but we didn't have any collisions, right? So I don't think we had any collisions. So you have the doorway. Okay, here's our doorway, and here comes one person, then another, and another, and another, and another, and another, and all their paths are crossing. But as long as all their times are a little bit different, we won't have any collisions, right? So these objects won't actually meet unless their paths cross. Okay? So here's what's kind of cool about this. Even though we're kind of considering it in a two-dimensional plane, we're actually dealing with 3 dimensions here. Just not the 3 dimensions we're used to dealing with. We're dealing with length and width, and then the 3rd dimension in this case is time. Okay? Time. And time is known as what's called a parameter, and we'll look at that more specifically later on here. Okay? But what we're talking about here is positions of objects that are moving at a constant velocity. Alright, if you got into an upper level math class, maybe in college or whatever, you might look at these when we have changing velocities. Like for instance, something gets thrown up in the air. Okay? Its position in terms of time, because our velocity will change as a result of gravity, we couldn't necessarily do this. But for our purposes here, we're just going to consider a constant velocity. And what we have is this vector equation. Okay? Here's our vector equation. R equals A plus TB. Okay? Now notice, look closely here because we use bold to indicate the vectors. R is a vector. This is the vector equation of a line. A is a vector and B is a vector. T is just a scalar here. Okay? T is a scalar. Now, what do all these represent? Okay? Well, R is your position vector at any given time. Okay? And I should probably put the word vector in there. It's a position vector. Okay? So sometimes you'll see it just called a point, and that's okay too. I'm using position vectors because that's what's actually in your formula book, so I want you to get used to using that. Okay? So R is a position vector from the origin to a specific point. A is the position vector at time 0. You can think of this as your starting point. Okay? So here was Eric's A, his starting position. Okay? B is our velocity vector. Okay? And then T is the amount of time that's elapsed. Well, one thing that's important to recognize about time is that it's kind of arbitrary. In other words, we can start the clock whenever we feel like it. So it is possible to have negative values for T. That just means it occurred before we happen to start timing it. Okay? So we can actually use negative T's to figure out where something has been in the past. Okay? Before we actually looked at it or whatever. Alright. Now, there's a couple of different ways to express this same equation. This is one, the vector equation. there's another one using component vectors. Okay, the component vector form, and that's just kind of my name for it. It doesn't really have a specific name, but here we have a position vector xy. We have our position vector x sub naught y sub naught for our starting position, and then we have this velocity vector AB. Okay? So x sub naught y sub naught is our position at time 0, t is the time again, and then AB is our velocity vector. So it's another way you'll see this same equation written. The last variation of this equation is actually a pair of equations. This pair of equations, I mentioned that t was a parameter, okay? T is an additional factor that we're looking at this beyond just position. We're looking at the time it's at a specific position as well. So we call it a parameter, all right? These equations are what are known as parametric equations. You can see that root word for parameter in there. Okay. Parametric equations. And what these two equations do is they break the vector form of the equation down to look at just the horizontal component and the vertical component in two separate equations. So those are our parametric equations. And do be careful that, if you're asked for the equation of a line, make sure you give it in the correct form. All right. So let's consider an example here. We have this vector equation for a line. xy equals -2, 5 plus t times 2, -1. And one of the important things is here to make sure that we identify the different parts of this equation properly. Okay. So what would our starting position be? Cameron?
-2, 5.
Yeah, -2, 5. That's our starting position. -2, 5. Okay. Then we can identify our velocity. What would our velocity be for this object? Okay, 2, -1. Now,
That's the
you said -1/2. Well, actually, -1/2 would be what in relationship to this line?
the slope.
The slope, okay? So this velocity vector is related to slope here, okay? Your vertical change over horizontal change. So every unit of time, we do have a slope of 1/2. We're using a vector because we could have a velocity of 4, -2, and while that line would have the same slope, and this velocity vector would have the same direction as this velocity vector, what would be true about this velocity? Same direction, but what? It's doubled. So while these two lines would be going the same direction, this one would be going twice as fast. Okay? So slope is related to velocity vectors, but it's not exactly the same thing. Okay? Alright. Now we can also write parametric equations from from this equation here. Remember, we should have two parametric equations, one for x and one for y. Alright, so how could we express x in relation to this vector equation? Good. -2 is our horizontal starting position. 2 is the horizontal component of our velocity, so -2 plus 2t would be the x parametric equation. Does everyone see where we got that from? Alright, now how about our y parametric equation? What would that be?
Y minus t.
Yeah, 5 t times -1 is minus t, so 5 minus t. Good. So you're just looking, horizontal components give you your x parametric equation, your vertical components give you your y parametric equation. Okay? Alexander, you feeling okay? Alright. Try to stay focused here. Alright, so here's a question. Where are we at these different times? Okay? You can go back to how you first started finding points and whatnot with your x and y table, but you need to incorporate time now as well. We have 3 dimensions. So we find these different points, okay? Where are we when the time is 0? Yeah, that's our starting time, right? So our starting position was -2, okay? If you plug in 0 in both of these, you get -2 and 5. So where are we when the time equals 1?
0.
Okay, 0 and 4, good. -2 plus 2 is 0, 5 minus the 1 gives us 4. Let's see, how about when t equals 5?
8, 0.
8, 0. Okay, 5 times 2 is 10, -2 plus 10 is 8, and then 5 minus 5 is 0. Good, 8, 0. And then, what about 2 seconds or minutes or whatever before we started actually looking at it? Where was it?
-4.
Wait.
Negative
7.
seven.
-6, 7.
Yeah, -6, 7. -2 plus 2 times -2 is -4. So -6, and then 5 plus 2 is 7.
Is nothing.
Okay? So we have a number of points here at different times. And guys, if you're drawing these, you should put the time next to each point. Alright, if I were sketching this, I would have -2, 5, and I would put there next to it t equals 0. Okay? And then I have the point 0, 4, and next to it I would put t equals 1. Alright? And then 1, 2, 3, 4, 5, 6, 7, 8. 8, 0 has a t equal to 5. And -4, -7, we would have t equal to -2. Okay, so here's our line. Okay, and we could keep, it could extend forever in both directions as well. Alright, but you would always put a time to go along with each point. Okay? And that is required. Alright? Otherwise, there's no difference in this or in another graph or a regular line. Okay? Yes?
But we don't need to put the coordinates, correct?
You don't need to write the coordinates yet, but you should give the time. So, you can see the coordinates, you can't see the time, so that's why. Alright, so what's kind of cool about this is we're dealing with 3 dimensions, just a little bit different way of dealing with 3 dimensions. Okay? Now, we can also use this to figure out something like this. Hey, I want x to be 10. What time is that going to happen? And what y value am I going to have when that happens? Okay? You know, here's at 8, 0. So, if I stretch this out, you know, here's x equals 10. If I draw this line going on down here, really, what is that point? That's what I'm finding. Okay? How would I go about doing that? What do you think? Plug in 10 for x, and that'll give you what? That'll give you your time. Okay? And the time would be 6? Yeah. Okay? So good. This is where the parametric equations come in handy. We plug in 10 for x. That's -2 plus 2t. We get t equal to 6. Alright? So I know this point has t equal to 6. Now I just need to find the y coordinate. Alright, well, using our other parametric equation, y equals 5 minus t. Alright, well, 5 minus 6 gives us a y equal to -1. And we can see that does make sense, at least from our drawing. Okay, so this right here is our point 10, -1 at time 6. Okay? So it's not always just plugging in a t value and getting your x and y. Sometimes you have to plug in one of the other values and you can figure out the other two. Okay. Does anyone have any questions about using this so far? Okay. So we found a bunch of points where this line hits. A little different question is this. Does this object actually hit this point? Do we actually go through the point 2, 3? Now, if we wanted to figure that out with our regular lines, we would have just plugged in 2 for x and 2 for y, and as long as we got it equal on both sides of our equation, we know it worked. Okay? That's not going to necessarily work here. How would we go about figuring out if that point's on the line? Jay, what do you think?
You could plug 2, 3 into the xy portion.
Mm-hmm.
The component vector form. And then how could you solve from there?
That's kind of the challenge here. If we plug in 2, 3,
You can can make different parametric equations from this. So you can have
We can make two different parametric equations, because here's the thing, you can't solve this equation as is. Alright? However, you could solve the parametric equations.
x equals 2.
So 2 equals,
-2 plus 2.
okay? And 3 would equal,
5 plus or minus t.
alright? Now, how would we then know if the point's on the line?
If the time is measured in a full second interval, I guess you get a single non-decimal.
We're allowed to have decimal times. You know, we could go for 1.4 seconds or something like that. Vanessa, what were you saying? Or I'm sorry, not Vanessa.
Amanda.
Amanda, I'm sorry.
Maybe if the answers are both the same for each equation.
Okay. If the two times are the same. In other words, guys, to be at a specific point, the x has to equal 2 and the y has to equal 3 at the same time. Okay? Because here's the thing, x is gonna be 2 somewhere, and y is gonna be 3 somewhere. I mean, the domain and range for a line are all real numbers. Okay? So, when you solve this, what do you get for your time? No?
You get 2.
We get 2, okay? Add 2, divide by 2, and we get 0. No, you got me saying it. We get 2, okay? What do we get on the y equation? 3 equals 5 minus 2. Okay? So, since the times are the same, okay? Since the times are the same, I know x is 2 and y is 3 at the same time. Therefore, I know it actually hits that point. Okay? So our line does hit 2, 3. Okay? You could say when t equals 2, just to be thorough. Okay? Alright. Does that make sense? Alright. Now, we've seen this with other things that we've done with vectors. When we move from 2 dimensions to 3 dimensions, we move from the plane to space, okay? The formulas are almost identical, okay? We just include that z component, alright? We find the same thing holds true here when we're dealing with our vector equations and our parametric equations. Alright, so let's take a look here. In 3D, which is really real life, which is 4 dimensions, right? We have 3-dimensional space along with time, okay? We have the same vector when it's written this way, r equals a plus tb. But when we see it written out in its component form, you see the z component. X, y, z equals x sub naught, y sub naught, z sub naught, plus t times abc. And you see your parametric equations as well. we construct them the same way, we just have that third one that we have to deal with now too. Now what is x sub naught, y sub naught, z sub naught? In a given situation, that's going to be
Position at 0.
position at time 0. Good. Our starting point. Okay? When you start the clock, that's where we're at. Okay? ABC is our what?
Velocity vector.
Yeah, it's our velocity vector. Okay? So again, it's set up just like the ones we were just dealing with. Okay, you have your starting point plus t times the velocity vector. Okay? And then we write our parametric equations, x sub naught plus at, y sub naught plus bt, z sub naught plus ct. Okay, and that'll give you your x, y, and z positions. Okay. Now, as you can probably anticipate, getting two things to intersect when we're in 3 dimensions, or 4 dimensions now, is a little bit more challenging. Okay, we saw with Eric and Jay, you know, just getting two things to intersect at the same time on a flat surface is hard enough, okay? But once we throw in the 3rd dimension, to get this all in space, you know, you can see it's much more complex. What's amazing though is that our brains are able to handle this incredibly fast, okay? If you think about just throwing a ball, you know, throwing a football to a wide receiver running a route, okay? You have your vector with the ball going to him. You have to get it at the right height, the right horizontal and vertical position, okay? He's got to be running that route, so you've got that intersection, and not only that, but you have to get it there at the same time he's going to be there, okay? It's really an amazing thing. No one in first period had done this. Have any of you actually shot skeet or clay pigeons? A couple of you have? It's a lot of fun. You ought to try it sometime if you've never done that before. That's kind of a similar idea. You've got this clay pigeon that's thrown up into the air, and it's moving through space, and obviously time is involved, and then you have the gun, and you've got to shoot it out of the air. So you have to think about the velocity of your shot and where it's going to go so that your shot gets to the same position in space at the same time the skeet does. It's really kind of incredible to think about. Your brain is able to process all this at once. Okay? Oh, where'd it go? Real quick here, one last thing. How would we find the angle between two lines, assuming they intersect?
It's not that formula we give.
A cosine.
Cosine theta equals u dot t over the magnitude of u dot t.
Yeah, what would we use then for our u and v?
The vector.
The velocity vector. The velocity vector. Alrighty. Have a great weekend, guys.
You too.